Hello everyone, my name is Tomasz and I'll talk about our work on finding the hardest formulas for resolution. The motivation for this work can be summarized by the following question. How hard can it be to prove a formula compared to its size? So our setup is propositional logic. We're working with CNF formulas, which I'm sure most of you are familiar with. And as the title suggests, we're working with a proof system called resolution. So every unsatisfiable formula has a resolution proof. If you're not familiar with resolution, it consists of one single resolution rule, which tells you that if two clauses clash on a variable, you can remove the variable and take the union of the rest of the clauses. And the resolution proof of a formula is simply a sequence of clauses that can be derived by a resolution, such that the last clause is the empty clause. And the resolution hardness of a formula is simply the length of a shortest proof that a formula has. The resolution hardness is interesting because it gives a lower bound on the running time of modern set solvers based on conflict-driven clause learning, and as such it has been studied a lot in proof complexity, and many families of hard formulas such as the pigeonhole principle are known, so families that require super polynomial proofs in resolution. So, but here we take a slightly different approach and we look at the resolution hardness exactly. We ask this question: how hard can a formula with m clauses get? So we define the resolution hardness numbers. So the mth resolution hardness number hm is just the length of the largest proof length the formula with m clauses requires. So this is really some sort of exact version of proof complexity. And our goal is to understand how these hardest formulas look, how fast the resolution hardness numbers grow, and possibly discover patterns that can be generalized to infinite families of formulas. Okay, one remark, we could also define the hardness numbers in terms of the number of variables, but that would not be very interesting, and you can check that in that case the hardness number would simply be 2 to the n plus 1 minus 1. All right, so our contributions in this paper are threefold. First, we do some candidate filtering to theoretically to narrow down the search space for hardest formulas. So we determine a small set that must contain some hardest formula with m clauses. Then we do symmetry breaking search using the graph isomorphism package Naughty to compute the sets chi-m that contain the hardest formulas up to the value of m equals 10. Finally, we compute shortest proofs of all the generated formulas using a novel set encoding that we propose for this problem. And so below you can see the values of the hardness numbers. The reason why we stop at m equals 10 is that both the formula enumeration phase as well as the computation of the shortest proofs of the hardest formulas become a bottleneck at this point.
Hello everybody, my name is Romy and I will present you our work on constraint-based software diversification against code reuse attacks. Software development today is based on uniformity, where end users execute identical binaries. However, this facilitates large-scale attacks. For example, assume multiple users running identical binaries, then an attacker is able to design an attack against this binary and successfully attack all these users. However, if the users run different binaries, then the attacker will not be able to successfully attack all the users. So our approach is to generate a large number of variants that are function equivalent but have different implementation. And at the same time, we want to control the quality of the generated variants with regards to the execution time or code size. In this work, we use a constraint-based compiler backend, in particular Unison, that takes as input the function in C code and outputs the optimal implementation in assembly code. Unison implements two low-level transformations, instruction scheduling that uses the cumulative constraint, and register allocation that uses the geometric packing constraint. Here we have the factorial function as example that, given as input to Unison, will generate the optimal solution that corresponds to an implementation of the function in assembly code. However, there are other solutions to the model that are not necessarily optimal. For example, here we have another implementation which has different register assignment for this operand, and the last three instructions are delayed by one cycle, resulting in an OP operation. So our approach is to generate a large number of variants that correspond to solutions to the constraint-based compiler backend. And to do that, we use a form of large neighborhood search around the optimal solution, which we also use to control the quality of the generated variance. Our results show that large neighborhood search is a promising approach for finding diverse solutions in CP. We studied the trade-off between quality and diversity and show that our approach to diversity by construction is effective against cold reuse attacks. If you're interested in our work, please watch our full video or read our paper. Thank you.
Hi everyone, thanks for having us. Today I'm going to talk about our paper, Computing Optimal Decision Sets with SAT. First, let's talk about the problem. The world has been changed by recent rapid advances in machine learning. Most machine learning algorithms are opaque, unable to explain why decisions were made. As machine learning is increasingly used to help make decisions, there is a demand for these decisions to be explainable. Arguably, the most explainable machine learning models use decision rules. This paper focuses on decision sets, a type model with another rules, which explains each decision with a single rule. Let's look at the example. There are 4 features and 8 items here. A valid decision set for this data for the class H would be this. If L is true, then class H is false. If L is false and C is false, then class H is true. If C is true, then class H is false. Also, in order to be easy for humans to understand, these rules must be concise. We consider a better measure compared to early work, namely the total size of the decision set in terms of the literals. The size of the decision set is 7. We provide the first approach to build decision sets by directly minimizing the size required to describe them. The iterative set model and method model can build perfect decision sets that match the training data exactly, or the method model can build sparse decision sets that trade off accuracy on training data for size. To assess the proposed set-based approach, a number of state-of-the-art algorithms were additionally considered, including the heuristic methods CN2 and Ripper. They don't guarantee any optimality, and their closest competitor, set-based minimal decision sets, but they first optimize the number of rules and afterward the number of literals. The method-based approach Int'l is also considered. They minimize the number of literals given some number of rules, but the only one to minimize the total number of literals. The figure shows that the winner of testing scalability is Ripper, which is able to train the most considered datasets. Our sparse model ranks second. However, the worst approach is our perfectly accurate decision sets. Regarding the testing accuracy, our perfectly accurate decision sets beat other approaches, and our sparse decision sets rank 4th. The worst accuracy is demonstrated by CN2. Finally, from the perspective of interpretability, the winner is our sparse model. It's not surprising that perfectly accurate decision sets in general tend to be larger. Thanks for listening.